We are ready. I think we can start, right?
Okay, just let me know when I should screen share. I don't see Anish, but you think we should go on?
Hi, Sebastian. This is
Yes.
Shiladitya.
Okay.
Please share the screen and start your talk.
Perfect. Perfect. Yeah. Let me do this. Okay, you can all see it. You're right. You can see the screen, right?
Yes, we can.
Okay. Okay. So, well, let me start by really thanking you for this very nice invitation to give a talk at this seminar series. So I will talk about inflation in a slightly unusual manner, in the sense that I will go beyond perturbation theory in this talk. So the talk will be based on works, three people who are here, Paolo Criminelli, Giovanni Tambalo, and Vicharit Yingcharenrat. And the talk is based on these two papers from 2024 and from a few months ago. So I usually like to say that primordial cosmology is like a detective story. The idea is that all the structures in the universe are inherited from inflation fundamentally. And so any observation of the cosmic microwave background, the large scale structure, or gravitational waves, and they give us a probe, more or less convoluted, of the statistical properties of the fluctuations left over from inflation, primordial density fluctuations and gravitational waves. And so the game is to compare observational data to theoretical data to deduce the physics of inflation. And typically, what is done is to work in perturbation theory, simply because primordial density fluctuations are small, as we see, as we know from the CMB. So we work in perturbation theory, assume a flat Friedman-Lemaitre background and consider small fluctuations. And out of that, we predict the statistical properties of these fluctuations. So the 2-point function, maybe the 3-point function that we compare to data. And this is a fantastic approach that has had great success. But in this talk, I want to do something else. I want to go beyond perturbation theory, and I want to show an example in which there is lots of information in a large endpoint function. By this, I mean not just the power spectrum and bispectrum, not just 2 and 3 point, but let's say 6, 7, 8, 9 endpoint function. And that's quite unusual. So here's the outline. First, I'll give some motivations to do these unusual things. Then I will explain how to go beyond perturbation theory, what is the method we're using here. And then I will go into details of the subject in these two parts, computing the so-called wave function of the universe for a specific class of inflationary model, and then point out a new regime where these large endpoint functions become relevant. All right, so the motivations, they are of different kind. basically phenomenological as well as theoretical. So the first question, as I already alluded to, is, well, why do you want to go beyond perturbation theory, given that inflation seems to be perturbative? CMB, for example, the Planck satellite developed here at IAP, told us that parameter fluctuations are pretty much Gaussian, with very small deviations in non-Gaussianity that have not yet been detected. And so the simplest explanation is a very weakly coupled theory, for which perturbation theory is perfectly fine. The catch is that this is only true for typical fluctuations. So I can see this plot as a rule of thumb. This shows typical would-be histogram or probability distribution function of the primordial density fluctuations, delta rho over rho. So I will use a symbol zeta used in this field to talk about that, the gauge invariant curvature perturbation. And usually what is done is to consider a framework in which this probability distribution function, this PDF for short, is a Gaussian plus correction. Okay, and these corrections are the 3-point function, the 4-point function, here schematically written. And you can see that actually this expansion, so this is a number times zeta, this is a number times zeta squared. So actually, the expansion parameter depends on the size of zeta. The expansion parameter is not FNL, it is FNL zeta, or GNL zeta squared, etc. So the point is that perturbation theory is perfectly fine close to 0 values for standard values of zeta of order square root of the Broad spectrum, but this will fail to converge and to have any meaning for large zeta. So typically when this quantity becomes of order 1, so let's say when zeta becomes of order 1 over FNL typically, or any other related quantity. So we need non-perturbative method, at least for one motivation, to study the tail of the distribution. So why would you like to do that? There are many reasons on different sides. One, for example, black hole formation is sensitive to zeta of order 1. Experts know that this is a bit more complicated, but to rare fluctuations for which we need, therefore, to take into account this information. Recall that FNL of order 1 is a typical prediction of most inflationary models, except if you want a single Filster roll, in which this would be epsilon, and therefore this would be very large. But as soon as you have a bit of non-Gaussianity, this threshold becomes relevant both for PBH, primordial black hole production, and dealing with the tail in a non-perturbative manner. Also, there can be surprise in the data on the tails, which have not been extensively studied. As I will describe, as already alluded to, there can be also unexpected regimes. Also, more on a theoretical side, it is just fun and very interesting. I will show you that one can compute in some regime the full wave function of the universe. And that's simply very nice to do out of pure theoretical interest. Also, maybe the tails and these non-perturbative methods can be relevant for total inflation. So that's a plethora of motivations. Now, on how to do it in practice, how to go beyond perturbation theory. I want to advocate the use of the wave function of the universe that I will describe, and the use of so-called semi-classical method. So the main idea is that inflationary fluctuations are of quantum mechanical origin. So these fluctuations are proportional to square root of h bar. We usually put h bar equal 1 in our computations, but it's really quantum mechanical. So when you look at rare, large fluctuation, the one that are on the tail, well, they correspond to large different occupation number. They correspond to large fluctuations compared to the typical one. And so somehow if you compare the two, it's as if you put h bar to 0 for this. And so you can already feel that it's a kind of semi-classical limit. And that's the whole point, that the tail of the distribution is amenable to a semi-classical treatment. I said it's still fully quantum for a reason that I will make precise, but what I mean by this is that the word semi-classical is very misleading. It's a word used in physics to mean that we will use an approach that looks like classical because there will be equation of motion, etc. But it's still fully quantum you can still compute things with that would be completely forbidden without quantum mechanics, like crossing a potential barrier that would be forbidden classically. Right? So that's a point of terminology, but that's important. So now let me introduce the object. I say the wave function. Strictly speaking, it's an abuse of terminology that I will still use. It's a wave functional. It is that the most primitive object in primordial cosmology is this. This is the wave functional. It's a function of a function. It's a functional. It's a function of the final value, the final field of zeta at late time after all scales that exist in the Hubble radius. And this can be formally defined as a path integral. This wave function is given by the path integral from all field configuration that are in Bunch-Davies in the past, because that's what we choose, up to that final configuration that we would like to know its properties, weighted by the usual exponential is. Here I reduce h bar to make it clear. So here this is a transition amplitude, again, from the Bunch-Davies vacuum to a given configuration. We usually don't use too much of the approach, but of course this can be related to correlators. If you know the wave function, you know the correlators. The correlators, let's say the endpoint correlator, will be the integral of the mode function squared, integrated over the many field realizations that are possible, and then you insert the n at zeta you want to characterize. So if you know the wave function, you know the correlators. That's the point. But it contains, if you want, this can be, this is a useful language to talk non-perturbatively. So you can also talk about the wave function in a perturbative manner. In that case, you will expand that object in series, and you will just want to compute wave function coefficients. And this can come with geometric rules, which are pretty similar to the way you would compute correlators. At least they're in one-to-one correspondence. But here we want to go beyond that. And the idea, as I said, is very simple. If you are looking at a rare fluctuation in which this object zeta bar is somehow large, it means that the action itself will be large compared to h bar. In that case, well, that's the essence of quantum physics and of the emergence of classical type behaviors. You can compute that by simply saying that the path integral will be dominated by the solution to the classical equation of motion that verify the boundary condition that I've mentioned, Bunch-Davies in the far past, and that finish on the final configuration zeta bar to which that I target. And effectively, if you compare to a perturbative approach, it corresponds to resumming all the tree-level diagrams, and you can show in this limit that loop effects are negligible. The loop effects in this computation will correspond to expanding around the classical solution here, and they will be negligible in the large zeta bar limit. And this has been pointed out in this paper. A few remarks now. Another popular approach that also talks about the tail of the distribution is stochastic approach. That's a very interesting approach, but I want to stress that what we're doing is radically different. Stochastic inflation only takes into account the non-trivial super Hubble evolution, but it trivializes everything inside the Hubble radius. Famously in stochastic inflation, the noise is Gaussian and wise, etc. Here we will be able to deal with genuine quantum physics inside the Hubble radius, and that's radically different. That's one point. Another point is that we will not just compute, let's say, the 1-point PDF, which is what is the probability that a given patch in the sky has this value for delta rho over rho. We'll be able to have full morphological information. For instance, and there is this nice picture that you may know where people see the Stephen Hawking signature in the sky, the CMB. One can ask this type of question, at least theoretically. What is the probability that such a shape of delta rho over rho, let's say, has compared, let's say, to the same shape, the same profile, but with a different amplitude? This we can answer. Are there any questions about that before I move on? Good. Okay. Let me make one technical comment. Let's already do that for a free theory. I assume perfect scale invariance for simplicity here and in the rest of the talk. For a free theory, the path integral evaluation through the semi-classical method is actually exact because it's a Gaussian integral. And so in that case, the classical solution is well known. You take the zeta bar profile you are aiming at, you Fourier transform it, and you integrate over the different Fourier modes, and this is reminiscent of the usual mode function in Butch-Davis. And this is the right solution that encodes the Butch-Davis behavior, because you can see that once you take into account the I epsilon prescription, so if you go in the conformal time eta complex plane, if you give a small positive and imaginary part to eta, this will decay in the far past. That corresponds to the prescription of imposing the right Butch-Davis vacuum initial conditions in the path integral. And so if you do that with this, you plug that into the action and you can compute it. You can do a trick, integrate by parts, and see that it only depends on the value of theta classical at the end. It's just a trick to make the integral. You plug that here and you find this result. And well, this factor is reminiscent of the scale invariant setup we considered. But you see also that you have this factor, which is divergent. When eta final goes to 0, final boundary of inflation, this diverges. But this is not really a problem, because this only affects the imaginary part of IS. But remember that for physical observables, we are interested in the mod square of to compute real, let's say, objects like correlators. The probability distribution function is the mod square of psi. So any imaginary part is irrelevant, and so you can forget that. In our more complicated examples, in which the theory is not free, this will also play a role. I will mention that as a side comment, but the way we deal with that is that we can subtract these contributions to deal with manifestly finite quantities, and that's fine because it does not affect physical observables. All right. Now hopefully the idea is clear. Let me move on with more meat. So I want to show you how we were able to compute this wave function for a specific, very interesting class of inflationary model called resonant inflation. Well, the first thing is that for this method, we need to have a classical solution, which is a classic solution to the equation of motion. So we need the full non-perturbative action first for zeta. And it's not known in general. As you know, typically, it's known in perturbation theory. You have to solve for the constraint, for the lapse, for the shift, you know, maybe the cubic, the quartic order action, not the full action. But here we need it. And so in the first paper in 24 that I mentioned, we were able to derive this very compact and simple, but very nice expression. This uses EFT of inflation. If you don't know, that's fine. Just think about pi as the fluctuating degree of freedom. Think about it as delta phi. It's if you want a nonlinear version of delta phi, the scalar field driving inflation. So this new non-perturbative expression is valid in all models of canonical single field inflation. It's a kind of resummation of the EFT of inflation. And this is valid in the decoupling limit. And the decoupling limit corresponds technically to taking epsilon small. And observations tell us that epsilon, observations is pushing to this limit because we haven't observed gravitational waves, and ns minus 1 is non-zero, so the data is increasingly pushing there. Non-zero eta, but small epsilon. And so in this limit, things simplify. It's as if you can consider a test scalar field on a rigid de Sitter space, or here pi in a rigid de Sitter space. And it's still perfectly consistent to have h dot here non-trivial. Okay. And the idea is that if h dot was roughly a constant, this would be just a free scalar field, d mu pi squared. And here, all the nonlinearities of any single field model of inflation, so any potential, is encoded in this function, and the nonlinearities that it gives to the action fully resummed, if you want. You give me a function h of t, h dot of t. Here is all non-linearities. It does also have virtue to make manifest the conservation of pi on super-Hubble scales. And so we shoot with a final value zeta bar, which is related to pi bar by a trivial proportionality constant h, which is pure constant because epsilon is taken to be small. So in the following, I will use the notation zeta for just pi up to that factor as an integration variable. So now we will apply that to a specific model. This model of so-called resonant inflation or resonant gaussianity has been studied a lot. The idea is simple. It's almost a single fleet slower model with a very flat slower potential, but you add to it a small but rapid oscillation. This gives rise to this time dependence for h dot. Remember that this was the crucial information that was entering here. H dot is roughly constant, that's the slower part, plus small sinusoidal corrections, cos omega t, with a small amplitude. That for historical reasons we call b tilde. I would say b for simplicity in the rest of the talk. So the regime we're interested in is small amplitude, but large frequency. So the omega here, the frequency of the beatings, is much larger than the typical frequency, typical linearity scale h during inflation. So we introduce this symbol alpha, which is large, large are large, for this high frequency regime, but small amplitude. And physically, this has been studied a lot. There is a resonance in these scenarios between these background oscillations in exponential I omega t with the oscillation of the quantum modes during inflation that oscillate like plane waves in conformal time. And this resonance gives peculiar features in the power spectrum, in the 3-point function, and also in a higher endpoint function. And this can be easily computed and understood. And you see this sinusoidal running of the gaussianity with an enhancement by some powers of half. All that to say that this is well understood in perturbation theory. So now we apply the method. There is a great simplification that we will work at first order in the amplitude of the feature in this parameter b. Okay, we will consider a very small amplitude. And there's the nice trick, the nice simplification is that then it's enough to evaluate the action that a priori we should evaluate on the full solution, on the zeroth order solution if you want, with no feature. And the zeroth order solution is very easy to get. So we evaluate the action with the correction, with the b here, or the b that enters here, but on the free solution, that's self-consistent if you want. Again, we subtract that unobservable divergent part that I already mentioned. And to deal with things numerically in an easy manner, we rotate to Euclidean times. Okay, so we go from eta to tau here, that is on the Euclidean side. And so the wave function, as a function of the profile zeta bar, is the Gaussian part plus a correction proportional to b tilde, and this is this part that we want to compute, correction to the exponent of the wave function. And here is the explicit formula. This looks a bit ugly, but it's actually already the result. This is delta s as a function of this profile zeta bar. You give me your profile for zeta bar. I know it's Fourier transform. I can compute, therefore, this zeta at all times in space through this. I plug that into that action, and I just have to make these integrals in space and time, and I have here my result for the correction to the wave function. And this can be done numerically, everything is perfectly well behaved, or analytically, so, in particular in the large frequency regime, where you can use a saddle point approximation. That's what we did in the paper. We did both. Now, what does this compute? If you compare to a perturbative approach, as I was saying, our results corresponds to resumming all tree-level diagrams at first order in B. Okay, this first one, second one, third one. And schematically, this can be seen as an expansion in what? In the size of the profile we are shooting at, zeta bar, times alpha squared. You can wonder about the loops, because we resum an infinite number of diagrams, but okay, what about the other ones? There are other diagrams at first order in B, which are loops. And this one, you can see that order by order, they are suppressed by a factor alpha squared times the parent spectrum. So the first line tells you that when zeta bar becomes larger than 1 over alpha squared, perturbation theory breaks down. You cannot just take into account the 2-point or the 3-point function or the equivalent for the wave function. You have to know everything. Here, note that we don't do that. We do not compute each diagram order by order and resum. We fully have the result from the scratch. That's important. And second, and that's a peculiarity of this model, when alpha squared p zeta is less than 1, you can neglect all loop diagrams, actually even for typical fluctuation. So the method that I described, which a priori is valid only in the tail, turned out to be actually valid also here for typical fluctuation. So it's a full wave function for large zeta bar or small zeta bar. It's a full object. Now in practice, what did we do? Well, you have to choose a profile. Remember, I said the wave function is a use of terminology. It's a wave functional. You have to give a shape for this profile and consider its probability. So for simplicity, we choose a given spherically symmetric profile, Gaussian, and we vary its amplitude. Here I use the same symbol for just the amplitude if you're of that wave. So there will be in the future one-dimensional plot where I just now vary one number. I went from a wave functional to a plot of a function because I fixed the shape. So the large zeta bar, you can see, corresponds to large peaks, small zeta bar to small peak, and negative zeta bar corresponds to minima, to trough, or to large ones. And again, what we compute and what we will plot is this delta S part. So the deviation here to the Gaussian part. Okay. And what do we find? We find very surprising results. This is the same plot, but the right zeta bar positive and zeta bar negative on the left on two plots. You see both numerical results and saddle point results for different values of alpha. The first thing I want to say is that the scales are very different. There is an asymmetry, which is huge actually, between peaks and troughs, which is completely unexpected for perturbations here. The second thing is, as expected from the argument of the resummation of the diagrams, as soon as zeta bar becomes of order 1 over alpha squared, we see something dramatic. We see an exponential growth. But now we can move on and go to larger values of zeta, right? Larger values, let's say, than 1-ish. And we see that in that case, of course, we do not expect an exponential growth forever. The growth saturates, and for different values of alpha, here are the results, very large values again, and we get oscillation on the tail, which is again perfectly unexpected from perturbation theory. And in the large frequency regime, we even have an analytical understanding of that through a saddle point evaluation of these integrals. And this is really non-trivial. This depends on the full shape of zeta, also on its Laplacian and so on. And importantly, there is an exponential enhancement on the right for zeta bar positive for local maxima that you do not get for local minima. You also have oscillations, but you don't have this exponential enhancement. A few comments. Well, the first thing is that it's really striking. We're saying that if you're looking at a very, very small feature with tiny amplitude, let's say b is 10 to the minus 10, this can have exponentially large effects on the tails of distribution. Of course, we worked at first order in B, so you can say, well, does it really commute? Is it fine to consider large zeta at all order in zeta somehow, but small b and only first order in B? And it's true that probably to have a robust quantitative understanding, we might need to go beyond that. But the fact that something dramatic is going in the tail is a fact. And of course, you can also do a full numerical approach to compute this at full or at any order if you want in B, and that's in progress. Also importantly, we arrive at a physical understanding of both this asymmetry aspect and this super resonance, the fact that this is a very large effect in alpha for peaks, using a toy model in quantum mechanics. With a toy model in which we have an harmonic oscillator with a perturbation that is time dependent and has similar properties, and we can explain and actually recover all the properties that I described. To put it short, the intuitive idea is that you start with an harmonic oscillator, you perturb it with a time-dependent perturbation that stops at some time. So at some point, it becomes an harmonic oscillator again. And you want to ask, what is the transition probability to go from the ground state, the Gaussian, to excited states? And it is very small, but the excited state wave function has both oscillations and has a much larger range than the ground state wave function. So this does explain all the aspects that we mentioned. I do not give lots of details here in the talk, but you can find them in the paper. Let's now move on with this new regime, inspired by this previous study, but distinct. So I first want to explain the motivation for that and give our results. So let me come back to this slide. Here, I explain that when zeta bar becomes of order 1 over alpha squared, we need to resum everything and we need perturbation theory breaks down. But what about if we need to do that for typical values of the power of zeta? So for values of zeta bar, which are square root of the power spectrum. So if we're in this regime, when this quantity becomes of order 1 or larger, we need the resummation, but even for typical fluctuations, not just the tail. If you express that in other language with other quantities, this corresponds to a very high frequency, omega, of the oscillations, which is larger than some factors for pi times f. F was this factor entering into the cosine that is giving these oscillations. And usually, it's really considered that, well, basically just do a Taylor expansion of this. It's more complicated, but you will see that f is a natural scale entering into this Taylor expansion, and that f, or a multiple of f, 4 pi f, should enter as the cutoff of the theory, at which point you cannot expand in perturbation theory. So you could say, well, this regime does not exist. We do not believe in this model for such large values of omega. But that's not really true. At similar times, we're working on this project. Hook and Ratanzi, in a paper in 23, pointed out that something actually very simple in spirit, although technically not easy. The cutoff cannot be 4 pi f, because when the amplitude b of the feature goes to 0, the feature disappears. It becomes a free theory. If the theory is free, the cutoff is infinity. So the cutoff cannot be 4 pi f. It should be corrected in such a manner that for b very small, the cutoff goes to infinity. And indeed, there are logarithmic corrections to the cutoff that goes in that direction. So this opens really this regime. Very interesting. When you have a very tiny feature, you have to go to very small b. But in that case, you can have a very large frequency, larger than the naive regime. And because we need to resum somehow more diagrams, it's a hint that there is a crucial information in large endpoint functions. So that's very interesting. Now, what did we do about that? Well, first, you really need to know what is the cutoff of the theory. This has been done in this paper, and if you want, we refine this computation. You take the end-to-end scattering amplitude of this model in flat space with this potential cosine of phi over f. With some work, you find the result. And it looks like you need a series with omega over 4 pi f. But also it decreases with some n factorial. This is at first order in B. That's why you have the B here. Here, I identified the center of mass energy of that process, which will really be E here, center of mass energy, with the oscillation frequency. That makes sense because the phenomenon of resonance that I described in resonant inflation occurs for large frequency inside the double radius. So that makes sense to compare the flat space scattering amplitude to this. And then, well, perturbative unitarity tells you that all this should be less than 1. You can do that analytically. You do that for any n, and you find what is the maximum value of omega that satisfies that. Or you can also do it in the high frequency regime analytically. We did both. You can find details in the plot. If you do it in the large frequency or large n limit, you will find that actually the maximum amplitude is actually when omega is much larger than 4 pi f, and in that case, this peaks at some large value of n, which is given by this. this omega over 4 pi f to the 2/3. And you can derive an implicit formula that gives you this cutoff. The important point is that this is the ratio between the cutoff and 4 pi f. So we want to see how it can be increased beyond 1. And here is the idea, is that, okay, this thing would be typically of order 1 or larger. But here you have this logarithmic factor that I mentioned, this log of 1 over b. So when b decreases, this grows logarithmically to the point that the cutoff is larger than what you think naively. Now, well, what are the endpoint functions? This can be computed very easily. For a small amplitude, there are only contact interactions that remain, and they're very easy to compute. And in the large frequency regime, we even get simple expressions. So this has been computed by Leblanc and Bayard 15 years ago. And the only point to get from this is that we know the result. We know the amplitude of the endpoint function, we know the shape, and therefore we're in business. And now, I did not give all the details, but the idea is, well, we want to look for that in the sky. So we look for estimators that estimate this parameter b that set the size of the non-causality of all the endpoint functions. And there are well-known techniques about that. Generalizations of what is known, maybe more well-known for the 3-point function. This integral basically computes the overlap between the theoretical signal, the theoretical endpoint function, and the signal in the sky. And we can compute out of that, out of this estimator. The estimator has a normalization such that it is unbiased. The average is the parameter b you want to estimate. And you can compute the signal to noise, which is just related to the variance of that object. This is for any individual endpoint function. You can also build an optimal estimator, which is a sum of all the optimal list of the estimators for each endpoint function with suitable weights such that, well, this is the optimal estimator that minimizes the variance. And skipping details, the total signal to noise squared for this optimal estimator is just the sum of the square of the signal to noise for each endpoint function. The real job was actually to compute this. And here I don't give details, I just give you straight the result. Here is the result for each endpoint function. Okay, it's b tilde squared because the signal was b and then squared. You have this omega over 4 pi f to some power, but you also have this n factorials that also appeared in the scattering amplitudes. The number of modes here is related to the number of modes that you have in your survey. That's important because if you have an infinite number of modes, if you can go to arbitrary large k, the signal to noise is infinite. You have infinite precision. So this does enter. And typically, for CMB and future large-scale structure surveys, it's a large number, 10 to the 7, 8, 9, let's say. And clearly here you see that when omega is greater than 4 pi f, again, this regime that exists, and that is very interesting, this grows. This initially grows with n. And later it decays because of this n factorial. And when approximately, analytically, the signal peaks, for which n, this is for the same n max actually as for the scattering amplitude. And at least you see that it's for large n max in the large frequency regime. And it's not just, analytically you can understand that it's not just one endpoint function that is large. It's actually many square root of n correlators that are overall similar. The best is to see that in the plot. That's my, I just have 2 plots remaining, this one and another one. Here are the signal to noise squared over the number of modes. So the true signal to noise, multiply that in your mind by 10 to the 9. So if you want this up above this line, this is detectable. We look at different values of the amplitude. The amplitude b diminishes from 10 to the minus 4 here to 10 to the minus 8. And for each value of b, we compute the cutoff exactly, and we push the theory up to that cutoff. We take omega to be there. And here is the signal to noise for each n. Because we have an analytical formula, we can plot it in a continuous manner. Of course, it makes sense only in a discrete manner. But you see the point. Here, you have a maximum signal for, let's say, the 4-point or the 5-point function. Here, when b is extremely small, 10 to the minus 7, the maximum signal is not for the oscillatory part of the 2-point function or the 3-point function, but for the 8-point function. So that's exactly what we were, the intuition we had, which is confirmed by our computation. Now the final plot. Here I was pushing the theory up to the cutoff. Here, there is a full information. Here, I vary both the amplitude of the feature from order 1 to small, and I vary at the same time the frequency in units of 4 pi f. The important point is that, okay, omega cannot be too large. The green region is excluded because the frequency would be larger than the cutoff. Everything below the green line is allowed theoretically. It's under control. The blue region corresponds to, in addition, having a total signal to noise greater than 1, so detectable. And the more you go on the right, the more the value of the signal to noise increases from bare detection, 1, to 10 to the 2, 10 to the 4, 10 to the 6. So the very important message is that in all this regime, you have theoretical control and a very tiny feature that give signal that is dominated here, that corresponds to these vertical lines, by the 3-point function, here by the 4-point function, here by the 5-point function, etc. So we have, in this 2D plane, frequency, amplitude, a whole region of very interesting new targets within reach, actually, of future surveys, as we explain in the paper. So let me recap and give some perspectives. I explained a generic method to compute the tail of the wave function of the universe non-perturbatively, and actually the full wave function in our example. These are the first analytical results of non-perturbative phenomena from, again, quantum mechanical interaction inside the horizon. There is really a rich phenomenology, which is completely absent that you cannot see in perturbation theory, this asymmetry, this super resonance, this oscillation in the tail. And again, in the last part, I highlighted this new regime with oscillatory signatures, which are mostly in large endpoint function and which are detectable.